let us start today's lecture. So, in previous classes, we have discussed about resource allocation and task scheduling in cloud computing. So, earlier classes, we discussed about the task scheduling algorithm in which the tasks are dependent in nature, right? While we consider the task, like if you take an example like this, A is the parent of B and also the parent of C. So if I consider A, B, and C, these are three different tasks, then you can see they are having precedence constants. Precedence constants means they are dependent on each other. That means when A is executing at the same time, you cannot execute B and C simultaneously. But once A is successfully completed, you can start task B as well as task C, right? But these are called as dependent scheduling. Sometimes also we call that as a workflow scheduling. So you can say task is categorized into two types. One is called as a dependent task. Another is called as independent task. Okay. So dependent task we generally represent in the form of an application, or sometimes we call the scheduling as a workflow scheduling. Okay, workflow scheduling. But here we need to consider also that some of the tasks are independent in nature. Right, it may be a mixture of independent and dependent. So there are different set of algorithms applicable if the tasks are dependent or independent in nature. Like dependent task scheduling case, we have already discussed about the round robin algorithm. We have also discussed about cloud list scheduling algorithm. We have also discussed about minimum completion cloud. Minimum completion cloud. Apart from this, also we have discussed about some of the measures through which also you can perform scheduling. Like I told you about top level and bottom level, static level, and also we have seen as late as possible, and we have also seen the concept of a critical path. Okay, so these are we have already discussed with respect to uh, dependent task, right? If dependent task is there, you can apply these algorithms or these performance. These are specially nothing but the performance measures. We cannot say directly these are algorithms. These are some of the performance measures we can apply in in a scheduling algorithm to take a decision. But whether it is a dependent task or a independent task, our objective is to order the execution of this task. Order means suppose T1, T2, T3, you are finding a order that is T2, T3, T1. That is a order. So you have to order this task in such a manner that the overall completion time, or which we call as make span, is going to be minimized, right? So we have seen these measures also. Make span, we have discussed about make span, we have discussed about utilization, and we have discussed about idle time, through which you can evaluate the performance of these scheduling algorithms. Okay, but in today's class we will focus on the independent task. Here the tasks are not dependent on each other. Like here you can find only one order, A followed by B followed by C. If I take this small application, then I need to execute A followed by B followed by C, or you can follow like this, A followed by C followed by B. There is no other order possible, right? But when you go for independent task, you may find number of orders. Like 3 tasks are there, like you can execute, if you go for all possible order, you can say B, A, C is also one order. B, C, A is another order. C, A, B is another order. And C, B, A is another order. So if there are 3 tasks, we have 3 factorial number of orders, right? That is 3 into 2 into 1. Okay, so it is equal to 6. So out of these 6 orders, one order will give you the optimal make span. Okay, or the better make span, you can say. But we cannot go for hit and trial method, right? Every sequence we cannot check to determine which order is going to provide us uh, better make span, right? That is practically not possible, because here you are looking for 3 different tasks, so you can make a conclusion. But when the number of tasks is huge, so it is not practically possible, right? So we have to come up with some of the solutions, right? How to order these tasks by observing the execution time of the task, and find a proper order, so that you can find a better management and utilization. So if you go for independent task or dependent task, you can categorize them into 2 parts. One is called as online algorithm, another is called as offline algorithm. Okay, or we sometimes refer it as a batch scheduling, right? And online is also referred as immediate scheduling. Okay, you can categorize a dependent task also into online scheduling as well as offline scheduling. So the difference is that in online case, suppose you are given like this, right? In the case of dependent task, you are given with a particular application like this. So once you are executing A, you don't have any knowledge of B and C. Okay, you take the decision of A. Once A is completed, once A is successfully completed, then only you can think about B and C. Right. In fact, round robin scheduling or cloudless scheduling or minimum completion cloud, these scheduling algorithms are not nothing but our dependent scheduling algorithms are nothing but the online algorithms. Okay. But offline algorithms, what happen? We have knowledge about how many tasks are there in a particular application. Right. For example, the entire workflow is known to you in case of offline scheduling. But when you go for independent task, for example, you have 3 independent tasks. One is A, another is B, another is C, right? And this they arrived in this particular order, right? So if you take 3 different tasks and they arrived in this particular order, so what I can say, in online algorithm, suppose you are picking task A, you don't have any knowledge of B and C. When you pick the task B, you don't have any knowledge of C. So that type of scheduling is called as online or immediate mode scheduling. But offline case, we assume that all these 3 tasks are available in the system. If all these tasks are available in the system, then you can choose one of the order. So out of these 6 order, we can choose one of the order. But if it is an online algorithm, there is only one order, that is A followed by B followed by C. So under online algorithms, we will see 5 different algorithms. One is called as OLB. It stands for opportunistic load balancing. Opportunistic load balancing algorithm. Second algorithm we'll discuss, which is a very famous algorithm, that is called as MET. Stands for execution minimum execution time. Third one is called as MCT, that is minimum completion time. Fourth one is called as KPB, that is called as K percent based. K percent based. And finally, fifth algorithm is called as SA, that is called as switching algorithm. These are the popular algorithms, and I'll also share the data set with you. I'll tell you about detail about this particular data set. You can simulate this algorithm. I'll tell a numerical example, but if you are interested to simulate it with a large data set, I'll provide you the data set and with a simple coding. This coding is very simple, so that you can use to run this algorithm in a large data set. Coming to offline algorithms, if you look into offline algorithms, we will discuss about three offline algorithms. The first one is called as mean. Okay, mean and mean. In fact, these algorithms are a single phase algorithm. You can say this is single phase algorithm, but these algorithms are two phase algorithm. Okay, that's why first phase we are taking mean, second phase also we are taking mean. Similarly, we have another popular algorithm that is called as a max-min algorithm. And third algorithm is called as suffrage algorithm. Again, you can use a large data set to evaluate the performance of these offline algorithms as well, right? So first we will discuss about online algorithm, then we'll discuss about the offline algorithm by taking simple numerical example. Okay, and obviously, if it is a two-phase algorithm, you have more knowledge. You have uh, assume that all these tasks are known to you, so you can change the order. But online algorithm, changing the order is not possible. The changing the order is not possible, and the number of the task sequence is predetermined. You have to follow a particular order. So while you are selecting a particular task, or while you are taking a decision about the task, so you have to choose an appropriate machine. All these algorithms are contributing in terms of choosing a particular machine. Okay. Offline algorithm, you have to focus on choosing a machine as well as ordering of the task. Okay. And if you look into the simulation result, I'll show you later, you will find that MCT algorithm is one of the best algorithm among all these online algorithms. Okay. And if you look into offline algorithm, mean is the best offline algorithm. That's why many research article, in fact, this scheduling algorithm starts from grid computing, but many people applied in the field of cloud computing also. So if you see, these algorithms are uh, used by various researchers in various fields, and they try to modify these benchmark algorithms to improve the performance, right? But standardized data sets case, you can see getting a result better than MCT in the online algorithm case, or min in the case of offline algorithm is very difficult or very challenging, you can say. Okay, so let us start with our discussion on the online algorithms. Then we'll go for the offline algorithms. So the first algorithm we'll discuss, that is called as opportunistic load balancing. So OLB assigns each task in arbitrary order. Okay, any order you are giving, any arbitrary order is you are giving, based upon that it is going to execute the task, but it is not going to determine any order. Okay, the order is already predetermined, but you can give any arbitrary order. So it assigns a task to the next cloud that is expected to be available, regardless of the task expected execution time on that machine. Okay, it is looking that which cloud is going to be available. It is a simple calculation you can see. For example, you have a work, you have to do a work W, and you have three resources, right? And when you look for the solution in the first resources, first resource is currently busy for 2 hours, right? When you look into third machine, it is busy for 1 hour. When you look into the third machine, it is busy for 30 minutes. That means before assigning the work W, these three machines, you can say M1, M2, M3, or C1, C2, 3, whatever may be. So they are busy for certain period of time, right? 2 hours, 1 hour, and 30 minutes. Okay. So if I assign the work W to machine 1, I have to wait for 2 hours. After 2 hours, machine is going to execute my task, right? But if I assign to machine 2, it will start executing my work after 1 hour. And but if the same work is assigned to M3, then it will start after 30 minutes. Like whenever you are requesting a call uh, to a customer care, like e-commerce sites, whenever you want to request call back, then it is showing a queuing time. It says that after 7 minutes, it is expected to get a call, right? Similarly, here we estimate this particular time. So the earliest one that is available here is that is M3, because if you go for M1 and M2, you have to wait for hours, but M3 case you have to wait for minutes. So what we have to do? We have to assign the task to the cloud that is expected to be available. So we expect that M3 becomes available after 30 minutes. So we can assign this work W to machine number 3. But we are not considering the execution time on that machine. How much execution time it is going to take? It may happen that the work one W is taking 30 minutes here to complete, right? 1 hour here to complete, and 5 hours to complete here. If you assign a particular work, let's say there is a machine, quite old machine, right? If you consider a very old machine, it will take more time. If you take a recent machine, then definitely uh, the time required to complete a particular task is less. So it is not looking into this expected execution time. Like it will complete around 5 hour 30 minutes. It is going to complete after 2 hours. It will complete our 2 hour 30 minutes. We are not looking into that. Simply we see which cloud is going to be available first. Accordingly, we are going to assign it. So the institution behind the OLD is to keep all clouds as busy as possible. Because if you assign to M1 or M2, okay, if you assign to M1 and M2, then M3 becomes idle. After 30 minutes, M3 has no work, right? So in order to make it busy, because after 30 minutes it will be idle. So if you give some work, it will be busy, and after 1 hour, M2 becomes idle. So you have to give some work to M2. So our objective is to make all of them as busy as possible. So that is a very simple algorithm. Just you need to determine this time and choose a machine. Choose a machine which is which is going to be ready at the earliest. But the problem is that OLB does not consider this task execution time. So the mapping it finds can result is very poor makerspace. So as we are not considering, our objective is to make all the clouds as busy as possible. But we are not looking into who can efficiently execute it. Okay, that's why it leads to very poor makerspace. But while you are taking a decision, sometimes what happens, you will find multiple clouds becomes ready at the same time. Like M1 is also ready, M2 is also ready at the same time. Then you can choose either of them randomly. One of the such cloud can be selected randomly, but it is better to give to the cloud having lower index. That means M1, M2, if there is a tie, then you give to M1. M2, M3, there is a tie, you give to M2. Okay. M1, M2, M3, three of them having a tie, then you give to M1. So you give to lower index one. So the mapper may need to examine all M clouds. For each and every task, we need to examine all the M different clouds to find the cloud that becomes ready next. Like for example, I have examined 3 different cloud here. I got 2 hours, 1 hour and 30 minutes. So I have selected 30 minutes, right? That is going to be ready next. So I have selected that. So for each and every task, if there are m number of machines are there, so in the complexity is order of m. Okay. For each task, you need to map to m different machines. So the complexity you can consider it as order of m. So let us take a small example to understand how actually these algorithms, this OLB algorithm actually works. Okay, let us consider that you have 5 different tasks. Let's say tasks are T1, T2, T3, T4, T5, and assume that you have 3 different clouds, C1, C2, C3. Some arbitrary time I am taking, like 89, 73, 50, 70, 80, 108, 285, 80, 301, 189, okay, 290 and 76. Then let's say 60, 97, 115. I have taken this time randomly, right? And assume that before executing this task, C1 is busy for 135 unit of time, C2 is busy for let's say 367 unit of time, and C3 is busy for 37 unit of time, okay, which we called as a ready time, right? Like you want to go somewhere, you reach to your friend's house, okay, but your friend is not ready. So he or she needs some time to ready, right? Similarly, whenever a task is reached to a cloud, it requires some time to become ready or to execute your task. We consider that as a ready time. So I've taken these raw values. So now if you apply the opportunistic load balancing OLB, first we'll see with OLB, then we'll go proceed with other algorithm. So if you consider 3 different cloud like C1, C2, C3, so they are busy for 135 unit of time, 367 unit of time, and 37 unit of time. So can anybody tell which cloud is going to be available first out of these 3 clouds, C1, C2, C3? Which cloud is going to be available first?
C3.
Yeah, the answer is C3. So without looking into the time taken in 3 different cloud by T1, what we have to do? We'll assign T1 to C3. Okay, if you look into here, T1 will give to C3 because C3 is going to be ready first. So if you give this, the ready time of C1 is not going to be changed. It is as it is, and C2 is also as it is. But the ready time of C3 is increased because it has to execute task T1. So whatever its ready time is there, now the ready time is updated. So we got 37 plus 50. So the ready time is updated to 87. Okay. So first task is now completed. So we are not looking whether 89 is the minimum one or 73 is the minimum one or 50 is the minimum one. Rather than we are looking in the cloud perspective. We are not looking in the task perspective. That is the main drawbacks of OLB, which results poor make spend, right? Now, similarly, when T2 comes to picture, I'm looking into the ready time of the cloud. And here you can see 135, 367, and 87 are the ready time. So the minimum ready time we are getting again in the C3. So we assign T2 to the last cloud, that is taking 108 unit of time. So in the previous case, if you see, you selected 50. So fortunately, 50 is the minimum time in 3 different cloud. But T2 case, the minimum time is in the first cloud, but we have given to the last one. Okay. So once you assign T2, again the ready time is not changed for C1 as well as C2, but the ready time of C3 is now changed. So it is 87 plus 108. So we are getting 195. Okay. So now you can see it is successfully assigned T2. That's why you can say the ready time is increased. But when you go for T3, Can you tell me in which cloud you are going to assign T3?
Cloud 1, C1.
Yeah, because out of these 135 and 367 and 195, the minimum one is C1. So T3 should be assigned to the first cloud. So it is going to take 285 unit of time. You may think, you can see also by looking into this data, you can say 80 is the minimum one, right? But as per this policy, we are not looking into that, right? But either m different clouds every time. Here our mapping is order of m. Here also our mapping is order of m. Here is our also order of m, because you are examining m different machine and selecting one machine for uh, assigning a particular task, right? So if T3 is assigned to C1, the ready time is increased from 135 to, you can say, 420. That is sum of 135 and 285. And C2 it is 367, and C3 it is 195. Now, similarly, if you proceed, T4 is assigned to the last one, that is taking 76 unit of time. So its ready time is updated to 195 plus 76. You will get 271. It is 367. Here it is 420. Okay, as it is, right? Because we have not assigned T4 to C1 and C2. So the same time it carry forward, right? Now, if you look into T5, again T5 is assigned to C3, because the minimum of 420, 367, and 271 is 271. So we have assigned T5 to the C3. So if you calculate this one, you are getting 420 here, 367 here, but I think it is increased to 271 plus 115. So it is 386. So what you can look into these scheduling algorithms, the order is not changed, right? The order is not changed, only assignment of the task to a cloud. We don't know which cloud we are going to assign, whether it is C1 or C2 or C3. So whatever decision we are taking, that is with respect to the selection of cloud, not the ordering of the cloud in the case of online scheduling algorithms, because the order is already predetermined. And irrespective of different algorithms, you have to take a decision how you are actually going to choose a particular cloud, right? Rather than finding their ordering, right? All algorithms will follow T1, T2, T3, T4, and T5 order. Order is not going to be changed. But somebody is looking into the ready time of cloud. Other sibling algorithms are taking so other decisions while assigning the task to the different cloud. Okay, so if I ask you what is the make a span here, so you can say make a span is nothing but maximum of three different cloud, right? Maximum among three different cloud. Right, C1 is busy for 420 unit of time, C2 is busy for 367 unit of time, and C3 is busy for 386 unit of time. So the maximum among these three is 420. So I can say overall make a span of these assigning these 5 tasks to three different cloud is 420, right? Similarly, if I ask you utilization, all of you know how to calculate utilization. Just I'm showing you an example. If I calculate utilization, you can say it is nothing but 420 plus 367. If I calculate average utilization, okay, average utilization 367 plus 386 divided by the overall make span into 3. So we are finding average just by taking the make span of all these three divided by 3. But as we are calculating from the overall time, that is 420, that's why in the denominator part I have 420. Okay, so 420 plus 367 plus 386. So this is 1173 divided by, if you do 420 into 3, you will get 1260. And if I calculate 1173 divided by at 1260, I think you are getting 0.9309, or you can say it is equivalent to 93%. So 93% of time the machines are busy, the rest percent of time they are idle. Right? As much utilization possible. If your objective should be uh, uh, your objective should be more as much as possible. Your utilization should increase. Right? Utilization is 93% means it is close to 100%. That is good for us. Right? If utilization is poor, then that is an inefficiency today. Similarly, make a spend you need to minimize. A lesser make spend, if you develop a particular algorithm where make a spend is, let's say, less compared to other algorithm, then definitely that algorithm is a better algorithm. Here you can see another example. The same example, just I have changed the data. So here I consider the cloud ready time, which I represent as by CRT, that is 89, 73, and 50 respectively. So you can write C1, C2, C3. It is 89, 73, and 50. Right? So if you take the first task T1, which takes 70 unit of time, 80 unit of time, and 108 unit of time in 3 different cloud. So if I calculate, if I select a particular cloud for T1, then you have to look into the earliest ready time. This is ready time, right? So I need to find the earliest ready time. So the earliest ready time I found is C3. So T1 is assigned to C3. So that is 108. So once you do this one, you will get 89, 73, and 158. Right? Now coming to T2, T2 is taking 285, 80, and 301 in 3 different cloud, but out of which you can see the best one is in C2, and fortunately C2 is the next ready cloud, right? 89, 73, 158. Out of them, the minimum one is 73. So we are going to assign T2 to C2. So it is going to take 80 units of time. Now it is 89, and this is updated to 153, and this is 158. Now if you go to T3, task 3, then it is taking 189, 290, and 76 unit of time. But we have to look into this ready time. There is no need to look into this matrix. So the ready time, the earliest ready time you can see that is 89. So T3 is assigned to C1. So it is taking 189 unit of time, right? So it is 8 and 7 and 2, right? And C2 is 153 and C3 is 158. Similarly, if you look into T4, the earliest cloud that is available among these 3 is your C2. So T4 is assigned to C2, so it is going to take 97 unit of time. So it is 278, and this is 0 and 1 means 5 and 2, and this is 158. So now you can see T4 is successfully assigned. We have another task, that is T5. So, but we have to look into earliest ready time. Earliest ready time we are getting in C3. So what I can do, T5 is assigned to the C3. So C3 is taking 37 unit of time. So it is 278 and 250 and 158 plus 37, right? So it is 5 and 9 and 1. Okay, so 195 unit of time. Now, if you calculate the make a spend in this situation, it is called as make a spend is the overall completion time, that is maximum of 278 and 250 and 195. So you will get the value as 278. Similarly, if you calculate the utilization, okay, utilization can be determined if you calculate average utilization. Individual utilization is nothing but 278 by 278, 250 by 278, 195 by 278. But average utilization, if you want to determine, that is 278 plus 250 plus 195 divided by 3 into 278. How much we are getting? Can anybody calculate and tell? Average utilization. So it is 278 plus 250 plus 195. So numerator part we are getting 723 and denominator part is 3 into 278. So we'll get 834. So 723 divided by 834, you will get 0.8669, which is equivalent to, you can say, 87%. So 87% of the time the resource is busy, rest of the time the resource is idle. Okay, is it clear? Okay, but the problem with this algorithm, as I already told you, that we are not looking into this execution times. Okay, we are not looking into this execution time. Okay, but we need to consider the CRT time. You can see in each and every case I have mentioned the cloud ready time. By looking into cloud ready time, we are taking a decision, which is not good. You take consider the cloud ready time, but at the same time you need to also consider uh, execution time only, right? That's why there is another algorithm that is called as minimum execution time. So this minimum execution time heuristic assign each task to the cloud that performs task computation in least amount of time. Okay. So out of these three different cloud, you have to select a cloud which is minimum among all the available clouds, right? And this heuristic is also called as limited best assignment. Limited best assignment, you are choosing the best one, right? You are choosing the best one among the available one. That's why it is called as limited best assignment, also called as UDA, that is called as user directed assignment. Okay. And this heuristic does not consider the cloud ready time. Okay. This heuristic, we are not considering the cloud ready time. Cloud ready time is not given to you. So you have to look into cloud ready time may be there in the, you can say, if a question is given to you, cloud ready time may be there in the system, but while it is assigning, it is not considering the cloud ready time. Okay, I'll tell you with the two examples so that it is more clear. And this heuristic can cause a severe imbalance problem. Okay, load across the machines. I'll tell you when I'll show you the real data set. Okay, real cloud data set or a real data set of the task scheduling. I'll tell you why it is causing the severe imbalance problem among all the machines, right? And the advantages of this method are that it gives each task to the cloud that performs it in least amount of execution time. That's why this heuristic is very simple. Previous one is also implementation is very simple. This case also implementation is very simple, right? Okay, so the heuristic needs order of m time to find the cloud that has the minimum execution time for a task. So like previous scheduling algorithms, also we have the complexity order of m, right? So you have m different clouds, then you are mapping to m different clouds, and you are taking a decision. Whether you take cloud ready time or you take minimum execution time, you have to go through all the m machines and choose a machine. right? So the complexity for each and every task is order of m. Okay, so let us see one example so that it will be more clear. So for example, if I take 4 different clouds, C1, C2, C3, C4, assume that cloud ready time is initially 0. We'll consider an example with all the ready time is 0. Then we'll consider also one of the, another example, we'll consider the cloud ready time so that you can distinguish these two. For example, for task T1, right? Let's say task T1, here we can see the details. Yes. Suppose task T1 is taking 20 unit of time in C1, 54 unit of time, 49 unit of time in C3, and 97 unit of time in C4. Similarly, T2 is taking, let's say, 74, 105, 81, and 93. T3 is taking 33, 87, 58, and 40. T4 is taking 51, 76, 69, and 123. Okay, so these are the 4 different tasks we have. So if you go for minimum execution time, let us see how we are going to assign it. So as initially cloud ready time is 0, so you need not worry. If cloud ready time is there also, there is no need to take care of that ready time because this algorithm does not consider the cloud ready time. So if you look into T1, T1 is taking 20, 54, 49, and 97 unit of time, out of which the minimum one is 20. That is in cloud C1. So task T1 is assigned to C1. Task T1 is assigned to C1, which is going to take 20 unit of time. Now the ready time of 4 different clouds are updated as 20, 0, 0, 0 respectively. When T2 is coming into the picture, T2 is taking 74, 105, 81, and 93 unit of time in 4 different cloud, out of which the minimum one is in cloud C1. So T2 is assigned to C1, that is taking 74 unit of time. Right, T2 is taking minimum in C1, so we are assigning in C1. So here you can see C2 and C3, C4 is completely idle. Even if they are completely idle, this MET algorithm does not consider that. Okay, it does not consider that. It simply ignores that. It chooses a cloud based upon this execution time matrix. You can say this matrix is called as execution, or you can say expected execution time. Expected time to execute, or that is called as ETC matrix, right? So we look into this matrix and we assign it. We are not considering the ready time. So T2 case, if it is taking 74 unit of time, then you can say now the ready time is updated to 94, and C2 is 0, C3 is 0, C4 is 0. And T3 case, suppose it is taking T3 case also, you can see 33, 87, 58, and 40 is there, out of which the minimum one we got in C1. So T3 is assigned to C1, that is 33. And based upon the minimum execution time, so the ready time is now updated to, you can say 7, this is 12, 127. Similarly, when you go for T4, again the minimum you are getting in C1 only, so we assign to C1, and it is now the ready time is updated to 178, right? So what you have seen in this example, there are some important observations, like all these tasks are assigned to the same cloud. That is one of the problem. That's why I told you this heuristic can cause a severe imbalance in load across the machine. Okay, it is a severe imbalance problem. While C2, C3, C4 are completely ideal, you are only assigning to C1. Okay, C2, C3, C4, they have not started yet. Okay, but you are giving more load to C1. Means one machine is completely busy while other machines are completely idle. That is not a good solution. So when you go for the real life data sets also, you can see there are some data sets are there in which one cloud is based irrespective of that different type of task. Means for each and every task, one cloud gives a better result. So in that case, what happens if you apply the MET algorithm, it will cause the imbalance problem, right? The load balance problem, imbalancing of load among the different clouds. So MET is a serious drawback if it is taking minimum time in only one machine, like this case. But if it is taking minimum time in different machines, somehow the load can be managed. But this is one of the worst case situation where MET performs poorly. Like for example, if I consider cloud ready time, for example, let us take another situation. If I consider the cloud ready time is 100, 20, 10, and 5 respectively. If you do this one also, T1 is assigned to the first one only, which takes a 20 unit of time. So the ready time is 120, here 20, here 10 and 5. Similarly, T2 will be assigned to the first one only because it is does not consider the cloud ready time. So it is now 194, 20, 10 and 5. T3 will also assign to C1 only. And write C1, C2, C3, C4. So it is taking 7. This is 2 and 227, 20, 10 and 5. Similarly, T4 is also case also it is taking the first one. So it is 8, 7 and 2, 20 and 10 and 5. It's because the ready time is 100 and total time you got here 170. So you are getting 278. So irrespective of the ready time, okay, we are not looking into the ready time. In the previous one, we focus only on the ready time, not in the execution time. And this heuristic is just opposite of that. We consider the execution time, but we are not considering the ready time. That's why it is called causing load imbalance problem. So whether OLB or you can say in this MET case, both cases you will face problem. Okay, if the data set is little bit uh, skewed towards to a particular cloud, your performance is not better in these two scheduling algorithms. So in order to avoid that, we have another scheduling algorithm that is called as minimum completion time. This is the third algorithm. So completion time means what? Completion time is the sum of the execution time and ready time. So you have already know what is execution time, like the time required to execute a particular task in a machine, on a particular machine, then that is called as a execution time. Before assigning that particular task, how much time a particular machine was is busy, that is called as a ready time. So you need to find the completion time, which is sum of execution time and ready time. Once you determine the completion time, it is, you can say, you are considering both factors. Like if you look into this particular formula, you can say the ready time is considered in the case of OLB. Execution time is considered in minimum execution time, and completion time is considered in this heuristic, that is MCT. So MCT takes the advantages of what? MET as well as OLB. It takes execution time into consideration. It also takes ready time into consideration in order to assign to different cloud. So here you can see MCT heuristic assigns each task to the cloud that results in the task earliest completion time. Previous MET case we say that the task which completes which is having earliest execution time. OLB case, we say that cloud earliest time, right? Earliest ready time, you can say, right? But this heuristic says that select a particular cloud that result task earliest completion time, right? So this causes some tasks to be assigned to the cloud that do not have the minimum execution time for them. Like previous example, I'll show you here. If I show you the same example which we discussed in the case of MET, then you can see in the MCT case how we have improved the performance. And you can see MCT heuristic is a variant of fast greedy heuristic. And MCT heuristic is used as a benchmark of immediate mode. I already told you this is considered as one of the benchmark. So any heuristic you want to develop as a part of your work, then you need to compare with the immediate mode heuristic. So the performance of other heuristic is compared against that of MCT heuristic. You don't need to compare with other heuristic, but at least you may compare, but MCT should be compared when you develop a new heuristic. So as a task arrives, all the machines in the heterogeneous computing suite are examined to determine the cloud that gives earliest completion time for the task. Okay. And like OLB as well as MET, here also it takes an order of M time to map a given task. Okay, the complexity is order of M to map or to select a particular machine in each and every heuristic, right? So if you look into this same calculation, let us do this calculation so that you can easily understand. Let us take 4 different clouds, C1, C2, C3, C4, and 4 different tasks, T1, T2, T3, T4, and the time is 20, 54, 49, 97, 74, 105, 81, 93, 33, 87, 58, 40, 51, 76, 69, 123. And this is MCT, right? And I can write the formula here. The completion time is nothing but the sum of, you can say, ready time plus, you can say, execution time. Completion time is equal to ready time plus execution time. Okay. So the ready time is not given here. So given a particular set of tasks, the ready time is not given to you. You consider the ready time as 0. So I consider the ready time of all the cloud C1, C2, C3, C4 is 0. Okay. Now coming to task T1. If you come to task T1, it is taking 20, 54, 49, and 97. These all metrics, whatever it is given to you, these are nothing but the execution time. But what do we need to find? You need to find completion time. So I'm copying this first row, that is 20, 54, 49, and 97. Now what you have to do, you have to calculate the completion time. Let me represent it by CT, this one by RT, and this one by AT. Okay. So CT can be calculated as ready time. So this is your RT and this is your ET. So if you sum these two values, you will get CT. So CT is nothing but 0 plus 20, you will get 20. C2 case you will get 0 plus 54, that is 54. And C3 case you will get 0 plus 49, it is 49. 0 plus 97, it is 97. So what we have seen in MCT definition, it says that select a machine or cloud which is resulting the earliest completion time. So in this case, you can see the earliest completion time is 20, right? Out of this 20, 54, and 49, and 97, the earliest time is 20, right or not? So we'll assign the task T1 to C1. Assign the task T1 to C1. Okay, T1 is mapped to C1. But what about this mapping you have done? C2 mapping you have done, C3 mapping you have done, C4 mapping is done. So this is undone. Okay, or this you have not assigned T1 to C2, C3 or C4. So this time you have to cancel out. So now what you can say, the ready time is updated as 20 for C1. C2 case it is 0. C3 case it is 0. C3 case it is 0. So try to understand it very clearly. So initially you have mapped to 4 different clouds, but finally you have assigned to only one cloud, right? You have assigned to only one cloud. So the cloud to which you are going to assign the task, there only you have to add the ready time. Other case you have to put 0 because you have not mapped the task or not assigned the task to that particular machine. So it is not going to result in the ready time. Okay, so next is again we consider for the task T2. Okay, to consider T2, that is nothing but the execution time of T2. So execution time of T2 is 74, 105, 81, and 93. Okay. Then what you need to find? You need to find completion time. Completion time is nothing but ready time plus execution time. So 20 plus 74, you know it is 94. Here it is 105. Here it is 81. Here it is 93. So you have added a ready time with the execution time. Now you got completion time. So you have to choose the minimum completion time. So the minimum completion time here you are getting is 81, right? Which one is minimum among all the 81? So we select this one and other mappings we have cancelled out. Because finally you have to assign to C3. So whatever time you are expecting in the other clouds, that is of no use. That's why we have cancelled it. So now the ready time is updated as 20. Okay, because before T2 it is 20. It is not 0, 20. Before T2 it is 0. Here it is 81. Here it is 0. Right? Now, if I write execution time of T3, execution of time of T3 is 33, 87, 58, and 40. Right? So if I determine the completion time is nothing but 20 plus 33. You know it is 53. Here it is 87. Here it is 9 and 8, 5 is 13. Here it is 40. Right? So we determine the completion time. So this is the expected completion time, right? So if something unusual happens, then it may delay the process also, right? But based upon the estimate, you have to proceed. So out of this completion time, you can see the best completion time is 40, right? So we have cancelled these things, right? This is of no use, right? Because we have not mapped to C1, C2, C3. That's why we have cancelled out it. Then you can determine again the ready time. Ready time before assigning T3 it is 20. Before assigning T3 it is 0. Before assigning it is 81. But after assigning T3, because you are going to assign T3 to C4, like T2 is assigned to C3, T3 is assigned to C4. C4, it is, if you assign it to C4, it is taking 40 unit of time. Right? Now ready time is updated. Again, you need to consider what? You need to consider execution time of T4. So execution time of T4 is 51, 76, 69, and 123. Right? So if you calculate their sum, okay, which is nothing but the completion time. Completion time you can calculate here. That is 20 plus 51 is 71. Here it is 76. Here it is 0 and 1. You can say it is 150. Here it is 163. Right? So which one is minimum? Which one is minimum here? C1 is minimum, right? 71 is minimum. Right? So these mappings are not done, right? So you have to cancel out it. Now T4 is assigned to which one? C1. So you can see now all the 4 tasks are successfully assigned to one of the cloud. So what is the overall completion time? If you see, again you calculate the ready time. So ready time of the first one, it is 71. C1 is 71. C2 is 0. There is no, you can see this mapping. There is no task assigned to C2. And the C3 case, it is 81. Okay. And C4 case, you are getting 40. Right? So can you tell me what is the make span here? What is the make span?
81.
81. That is the maximum of all. It is very easy. But calculating average utilization, you have to do calculation, right? The average utilization is nothing but 71 plus 0 plus 81 plus 40 divided by 4 into 81. Okay, many people skip this machine, but you include it, right? They skip this machine, but as we have not assigned any task to C2, but you need to consider it, okay? Because as a system, it contains 4 different machines or 4 different clouds, so you need to consider it. So I think you will get here 71 plus 81 plus 40. It is, I think, 192. And 4 multiplied by 81, I think you'll get 324. So 192 divided by 324, you'll get 0.59. So utilization is only 59%. So what is the make span you get in MET? Can anybody tell? If I go back to the slide. So this is MET calculation, right? How much you got here? 178. Forget about this cloud ready time. We have not considered cloud ready time in this case also. MCT case. Currently, we have not considered any cloud ready time. So you got 178. But what is the improvement over here? Here the improvement is make span is 81. So obviously the make span of MCT is better in comparison to the make span of MET. Right or not? So that MET is better in comparison to MCT. Sorry, MCT is better in comparison to MET because it is providing least make span value. Okay, can you reiterate this example by taking ready time is 100? What ready time we have taken in the previous case? I think we have taken 100, 20, 10, and 5. 100, 20, 10, and 5. C1, C2, C3, and C4. So try this one. Do the same example with C1, C2, C3, C4 as ready time. Ready time is 100, 20, 10, and 5 respectively. Otherwise, let me write a fresh page so that it will be more clear. So ready time is considered in 4 different clouds. Is 100, 20, 10, and 5, right? And T1, T2, T3, T4 in 4 different cloud entities, whatever we have taken, like 20, 54, 49, 97, 74, 105, 81, 93, 33, 87, 58, 40, 51, 76, 69, 123. So please solve this problem and let me know what is the make spell. This is MCT only. You calculate the make spell. Just you need to calculate by adding this ready time. So the result may be different. What we got in the previous one, that is make spell is 81. So in this case, you may get make spell is a different value. So I think you will get more than 81. So but let us see whether we are getting more than 81 or not. Okay. Have you solved T1? T1 is assigned to which cloud? Can anybody tell?
Assigned to cloud 3, C3.
Cloud 3. Okay. What about T2?
Cloud 1,
T3?
cloud 4,
Okay. T4? Okay, let us see one by one. T1, if I take T1, so T1 is taking 20 unit of time, 54 here, 49 here, 97 here. If I sum it, it is 120, it is 74, it is 59, and it is 103. Oh, yes, it is correct. 59 is the completion time, earliest completion time, and we cancel these mappings. And now the new ready time is calculated as 100, 20, and 59, and 5 respectively, right? Then if you go for T2, T2 is taking 74 unit of time, 105, 81, and 93. If you sum it, you will get 174, 125, 0, and 185 is 140, right? Yeah, 140, and this is 98. So the minimum one we are getting is 98. I hope you will get the C4, T2, mini. Am I correct?
Yes, sir.
Yeah. So it is not the C1, this is C4. Okay, so we'll cancel these calculations. Okay, and the operated ready time is again 100, 20, 59, and 98. Okay, then you take T3. T3 is 33, 87, 58, and 40. If you sum it, it is 133, and it is 107, and I think it is 117, right? 7 and 1 is 117, and this one is your 138. So you are getting the minimum one in C2. Am I correct? Meaning,
Yes, sir.
yeah. So it is assigned to C2, not C4. It is assigned to C2. Then again, updated ready time, we are getting 100, 107, 59, 98. So T4 is taking 51, 76, 69, 123. So here we are getting 151 is 3, and this is 8, 1. This is 8, 1, then it is 12, right? Then this is 1, then it is 22, right? 110, then 12 is 221. Okay. So the minimum one we are getting here is 128. So T4 is assigned to C3. So the final ready time is 100, right? Because no task is assigned to C1. And I think one task is assigned to C2, that is T3. C3 case, we have assigned, you can say 2 tasks, right? It is 128. And C4 case, you are getting 98, right? It's 100, 107, 128, and 98. So make a span, you can calculate where the maximum of these are, then you will get, I think, 128. So previous case it is 81, but now it is increased to 128. You can calculate average utilization, which is nothing but 100 plus 107 plus 128 plus 98 divided by, you can say 4 into 128. How much you are getting?
84%. 0.8.
0.44.
84, sir.
Yeah. So you will get 100 plus 107 plus 128 plus 98. So it is equal to 433 divided by 4 into 128. So 512. 433 divided by 512. 84% we are getting, right?
84.
Yeah, sorry. It is 84%. You will get 8457. So it is approximately 84 or 85% you can get. Right? So in this way, you have to solve the problems associated with the MCT. Okay. There is another algorithm that is called as KPB. And in fact, the KPB and the switching algorithm is a little bit complex. It is not simple as it is MET or OLB, or you can say MET, right? Because these are nothing but you can say combination of other algorithms. In fact, MCT also, it is a combination of MET and OLB, but it is simple. But KPB case, it is little bit complex than other algorithms. So let us see how to take a decision using KPB. So K% based heuristic considers only a subset of clouds while mapping a task. So earlier the complexity, what I told you, that is order of m. If there are m different clouds we have. So here the complexity is reduced to, let's say, order of n. Right? Assume that order of n, where you can say m is greater than n. So we want to instead of mapping to m different cloud, what we did here, we consider n different cloud, which is a subset of m. Right? For example, you have C1, C2, C3. let's say up to C10. Okay, 10 different cloud. But N is, this is your M set, okay? M is equal to 10. But I am taking only C1, C2, C5, and C7. By considering N is equal to 4. Right? So we consider a subset of cloud rather than the entire cloud. Okay, this is the only difference. Previous heuristics are mapping to all the clouds, but here we are considering only a subset of the cloud. Okay, so now the subset, how to form this subset? The subset is formed by picking the M into K by 100. Best cloud based upon the execution time for the task, where 100 by M is less than equal to K less than equal to. Let us consider M is equal to 4. We have 4 machines. And let's say K is equal to 50%. K percent based we are saying, right? 50% based. So M into K by 100. So this is nothing but 4 into 50 by 100. How much you will get? 4 into 1 by 2. Right? So you will get 2. That means subset is found by picking 2 best cloud out of 4 different cloud. Based upon the execution time for the task, where 100 divided by M. So 100 divided by 4 less than equal to K. K is 50% less than equal to 100. You see, 100 divided by 4 is how much? 25, right? So it is nothing but 25 is less than equal to 50 less than equal to 100. Okay, this condition need to be satisfied. You have to choose a value such that this particular condition is satisfied. That's why it says that picking 2 different cloud based upon the execution time of the task, where 25 is less than 50 less than equal to 100. Right? So you need not worry. Just you imagine that if there are 4 clouds are there, I am choosing 2 clouds. Or if K value I am taking as, let us take K value as 70%. Okay. You can say 75%. Let us take 75%. Then 3 out of 4 clouds I have to choose. 3 out of 4 clouds we have to choose. Okay. Now the task is assigned to a cloud. Okay. Task is assigned to a cloud that provides earliest completion time. You know, in MCT case, we deal with the earliest completion time only, right? But this earliest completion time you have to do with the subset, not with the entire set. For example, if you consider K is equal to 100, K is equal to 100 means what? 4 into this calculation will 4 into 100 divided by 100. So you will take whole set. You will take a whole set. So this you can say either 4 clouds are there in the original set. In the subset also you are taking 4. Sometimes we call that as the improper subset, right? It is containing all the elements as the set. That's why we call that as the improper subset. So if K is equal to 100, then KPB heuristic is reduced to MCT heuristic. If we take K is equal to 100, then KPB acts like our MCT heuristic. The principle of MCT is applied to KPB if it is 100%. But if K is equal to 100 divided by M, like here, K value is equal to, let's say 100 divided by M. M is 4. Let us take in our example, it is 4. So it is 25. Right? Then KPB heuristic is reduced to MET heuristic. Okay. It is behaves like an MET heuristic. That means KPB is taking both advantages of MET as well as MCT. Okay. So how to choose the value of K? It is really challenging. That's why a good value of K maps a task to a cloud only within a subset formed by computationally superior clouds. Choosing that K value is really a challenging process. And the purpose is not so much to match the current task to a computationally well-matched cloud, as it is avoid putting the current task onto the cloud which might be more suitable for some yet to arrive task. We are not fitting with the most applicable machine. Rather than we want to uh, avoid actually putting the current task to a specific cloud, okay, which is more suitable for some early the upcoming task, okay, some yet to arrive task means some upcoming task. Okay, so let us see one example so that this idea becomes more clear. So let me take the same example again. We consider you can say 4 different tasks, and let's say 4 different cloud times are again I'm taking same value I'm copying here: 20, 54, 49, and 97, 74, 105, 81, 93, 33, 87, 58, 40, 51, 76, 69, 123. Okay. Now, what I told, this is an entire set. Okay, you have knowledge of entire set, but if you go through the whole set, it is taking order of m complexity for each and every task. So actually, we need to avoid it, right or not? We need to avoid it. So what actually we want to do? You have to choose a subset of machines. In the previous slide, I told you if k value is equal to 100 by m. So here you need to define what is the k value. For example, we consider in KPB case, the value of k is equal to 50%. Okay. So if k value is 100 by m, m is equal to, let's say, 4 machine here, right? If k is equal to 100 divided by m, m is 4, 100 divided by 4 means 25. Then 25 means what? You have to choose the minimum machine. Like for T1, you have to choose 20. That is C1. T2, you have to choose again C1. T3 case also C1. T4 plus also C1. If K is equal to 25%. If K is equal to 100, then you will explore all the machine C1, C2, C3, C4 and choose a best machine among them. But here the K value is in between the MET and MCT. Okay. So when K is equal to 25% in this example, KPB is equal to MET. When K is equal to 100%, KPB is equal to MCT. But what we have taken, K value is 50%. So it will make a trade-off between whom? MET as well as MCT. So how actually we are going to process here? Let us take C1, C2, C3, C4. For C1, I will choose the best 2 machine. Best 2 machine is C1 and C3. Right? C1 and C3. As all the, you can say ready time on all the clouds is 0. So I'll map T1 with T1. As you know, the 2 best machine is C1 and C3. So I'll take 20 here, I'll take 59. Okay. So what I can say, it is 20 for C1, 49 for C3. I am not going to map because it is 50% means you will go for only 2 clouds, not all the 4 clouds. So I found the minimum is 20. Right. Now coming to T2, right? It is 20. So first cloud it is already executed. So ready time is now updated to 20, 0, 0, 0. For example, if you go for T2, the best the T2 has 4 different values, right? In 4 different clouds. But I am going to consider only 2. The best 2. The best 2 is 74 and 81. So here I'll write 74, here I'll write 81. How much you will get if you calculate the minimum completion time? The minimum completion time like in the previous case is 20, here it is 49, right? So I'm choosing the minimum one and I'll make it undone. So in this case, it is 20 plus 74, you are getting 94, okay? And 0 plus 81, you are getting 81, right? So which one you are going to choose? 74 plus 20 and 81. So obviously 81 is the minimum one. So I have to choose 81. Okay. Rest are 0 because we have not mapped. So the ready time is updated as this is undone because I have not assigned it. So 20 because T1 is assigned to C1. So that's why it is 20. And T2 is assigned to C3. That's why it is 81. Right. So now 2 tasks are assigned. Now come to T3. T3 case, the best 2 machine is 33 and 40. So I'll choose 33 and 40. So if I calculate the completion time, it is 53 here, 40 here. So I'll choose C4. So T3 is assigned to C4. So now ready time is updated to what? 20, 0, 81, 40. Right? Now when you come to T4, T4 can be assigned to 51 and 69. These are the 2 best machine among the all the 4 machine. So it is 51 here, here it is 69. So if you sum it, it is coming as 71, it is 0, and this is 0, 1, you will get I think 150. 90 plus yes, 150, and this is 40. Okay. So in the okay, not this is not 40. We are not going to count this one now. Out of which one is better? 71. So final ready time we are getting is 71. T4 is assigned to also C1. So it is 71. None of the task is assigned to C2. Okay. And if you look into C3, C3 it is 81, right? This is undone. Then the last one is 40. So if you calculate the make span, it is nothing but maximum of 71, 0, 81, and 50, which is equal to 81. Similarly, you can calculate average utilization is equal to 71 plus 0 plus 81 plus 40 divided by 4 into 81. How much you are getting here? Can anybody calculate? Are you getting the same value? This will come as 192. 81 into 4. You will get 324.
9%.
Yes. 59%. 0.59 in fact you will get 259. That is equivalent to 59%. So it is reducing the complexity. Right. You are mapping to only to not to all the clouds. You consider only 2 machines. So the data set, if you look into the data set, here you can, if you go for the data set, there is a data set called as consistent data set. In that consistent data set, you can easily find which column means in this case the clouds are considered as a column, right? Which columns will give you the minimum value. So because in fact finding the minimum value again needs all the values, right? If I ask you to find the minimum value in the first row, then if you find the minimum value in the first row, so you have to choose these 5 values, these 4 values, then only you will come to the minimum one, right? Similarly, T2 case, you have to choose the minimum one, right? After observing these 4 values, right? So Finding minimum is order always the complexity of order of n. Once you know all the m values, then only you can decide the minimum one, right? But if you go for the dataset, you will come to know this particular cloud is taking best one in the, especially in the consistent dataset. You will come to know this is the best one among all, and this is, let's say, the second column where you are getting best value for all the tasks. So in that case, it is more easy. The complexity is not order of m; it should be quite less in comparison to order of m, right? Okay, so we'll go for the last algorithm in this session. That is called as SA algorithm. SA is called as a switching algorithm. Again, it is taking MET, MCT into consideration. So the main motivation behind going for the switching algorithm is that the MET heuristic can potentially create load imbalance across cloud by assigning more tasks to some cloud than others that we have seen. All the tasks, that is T1, T2, T3, T4 in our example, are assigned to C1, right? Cloud 1. So cloud 2, cloud 3, cloud 4 is completely idle. So it creates load imbalance problem. Similarly, if you go for MCT heuristic, it tries to balance the load by assigning the task to earliest completion time. That's why load is balanced. Somehow, if you go for large data set, sometimes you can find MET is better than MCT, sometimes you find MCT is better than MET. But what we have observed till now, MET is creating load imbalance problem. MCT is balancing the load by considering the earliest completion time. So if the task arriving is a random mix means in some task, a particular cloud is better. For another set of tasks, there is a one, maybe one case C1 is better, another case C2 is better, another case C3 is better, and so on. So if the task arriving is a random mix, it is possible to use the MET at the expense of load balance until a given threshold, and then use MCT to smooth the load across the machine. So if we calculate the load, and based upon that, if we take a decision whether to go for MET and MCT, then it is possible to get a better result than MCT. Okay. So switching algorithm actually did that thing. Switching algorithm uses MCT as well as MET heuristic in a cyclic fashion. And this cyclic fashion depend upon the load distribution across machines. Okay. Sometimes if you feel that there is a load imbalance, it switches to MCT. If you feel that load is balanced, then it is switched to MET. Right? And the purpose is to have a heuristic with the desirable properties of both MCT and MET. These all algorithms are like KPB and SA, or in fact you can say MCT is also combination of two different algorithms. So in order to do this one, here we consider two important parts. Like let's say the maximum ready time over all the clouds is considered as Rmax. R stands for ready time and maximum is represented as Rmax. Similarly, minimum or the earliest ready time is considered as Rmin. One is Rmax, another is Rmin. And there is a load balance index across the cloud, which is calculated as pi. Pi is called as a load balance index, which is nothing but Rmin divided by Rmax. So this mathematics looks very complex to you, but it is too easy. For example, C1, C2, C3, C4. Ready time of C1 is 10, C2 is 20, this is 15, this is 35. You tell me which one is maximum? Out of these ready times, which one is maximum? Which one is maximum? C4. Which one is minimum? C1. So you know Rmax is nothing but 35. Rmin is nothing but 10. Pi is nothing but 10 divided by 35. That's all. The same thing is written in the first two lines. So the parameter pi have any values in the interval of 0 to 1. Obviously, maximum value is more in comparison to minimum value, or in the worst case, maximum value is same as the minimum value, right or not? So always the interval you will find in the range of 0 to 1. So if pi is equal to 1, that means what? Pi is equal to 1 means R min is equal to R max. Then the load is evenly balanced across the machine. For example, 10, 10, 10, 10. Now you tell me R min is 10, R max is 10, pi is 1. That means load is equally balanced among all the clouds, right or no? But if pi is equal to 0, 0 means let's say 10, 10, 10, 0. R min is 0, R max is 10. So pi is nothing but R min is 0, R max is 10, so it is 0. So if pi is 0, then at least one cloud has not yet been assigned a task. Right? You can see one cloud is not assigned in a task. Right? Now we consider two threshold value. One is called as pi L and pi H. What is the range of pi? Range of the pi is 0 to 1. So in this range, we consider one threshold as pi L, another threshold as pi H. For example, 0.2, 0.6. But while you are choosing this pi L and pi H value, make sure that pi L is less than pi H. Obviously, higher index is more than the lower index. Right? So initially, the value of pi is set as 0. We don't know the value, no? That's why we consider as 0. So SA heuristic begins mapping with MCT heuristic. How it starts mapping? It starts the mapping with MCT heuristic until the load balance index increases to pi h. You start with MCT until unless you reach to pi h point. After this point, what SA heuristic is doing? It is applying MET. Okay, this causes the load balance index to decrease. Okay, it will decrease. And when it is decreased to pi L or less, then what SS heuristic is doing? It switch back to MCT heuristic for mapping the task, and this cycle is continued. So if the value is greater than pi h, then you have to apply MCT heuristic until unless you reach the value less than pi L. So once you reach to pi L, then you have to again switch it to MCT. Right? Like that fashion, you have to iterate this algorithm. So if you take an example, the functioning of SA with the lower and upper limits are generally fixed as 0 0.9 respectively. You can take different values, but as an example, they consider the pi L value is 0.6, pi H value is considered as 0.9. And if you consider K mode is equal to 1000, that means total number of tasks considered in a particular situation is 1000. And one particular rate of arrival of task. So if I take 1000 tasks, the switch between MET MCT happens only 2 times. Sometimes we think that if the switching is more, like you have seen round robin algorithm, right? We are doing context switching. So if there is a frequent context switch, then it leads to an overhead. Similarly, frequently switching from MCT to MET, MET to MCT, it is also an overhead. Okay, just like you have to take a switch case. If the first one is true, you will go for case 1. If case 1 is not satisfied, you can go for case 2, right? That is from MCT to MET again to the MCT and assigning 715 tasks in MCT. So out of 1000 tasks, 715 tasks are assigned as for MCT. But when you take 2000, number of tasks is 2000 and same task arrival rate, then switching algorithm switched 5 times. Here it is switching 2 times in 10,000, 1000 tasks. 2000 tasks, it is only 5 times. Okay, using the MCT to assign 1080 task it is assigning based upon the MCT. Okay. So it is assigning MCT. By using MCT, it is assigning 1080 number of tasks, right? And rest are assigned using the MET, right? Minimum execution time. So let us see an example to clear this idea, right? So if I take an example, for example, I have taken 3 different clouds, C1, C2, C3. Let's say the cloud ready time is 89, 73, and 50 respectively. Why I am considering cloud ready time is here? Because you need Rmin, Rmax value. Until unless you know the Rmin, Rmax value, it is not possible to calculate pi. Once you calculate pi, then only you can take a decision. That's why CRT is mandatory in this particular case. T1, T2, T3, let us take 5 different tasks. And let's say the values are 70, 80, 108, 285, 80, 301, 189, 290, 76, 60, 97, 115, 135, 367, and 37. Now, you can see what is the, now, okay, I'm taking C1, C2, C3 here. The ready time is nothing but 89, 73, and 50. What is Rmin here? You need to calculate pi, right? Pi is nothing but Rmin by Rmax. So pi is equal to Rmin by Rmax. Tell me what is Rmin value? What is Rmin value? And what is Rmax value? Rmin value is 50, right? Minimum. Rmax value is maximum, that is 89. So if you do 50 divided by 89, you are getting 0.562. What is your range? Your range is 0 to 1. That is the value of pi. Okay. Pi L is here and pi H is here. Right? Let's say pi L we consider as 0.2, pi H 0.6. So now your value is in between 0.2 to 0.6. So you will start with MCT. MCT means T1 you take, T1 is taking 70, 80, 108. You calculate the completion time. Completion time, if you calculate 89 plus 70, it is 9 and 159. This is 385. Okay, this is 158. Okay, this is the completion time. Earliest completion time you will take in the case of MCT. So you choose this one and cancel these two. Now, if you calculate ready time, we have not assigned any task to C1, so it is 89. C2, it is assigned, it is 153. C3 case, it is 50. Right? Now, if you go for T2, T2 takes 285, 80, 301. So, if you calculate the completion time is, you can see here, I think it is, okay. So, before going to T2, sorry, I forget to tell you, T2 case, what you have to do? Again, you calculate the pi. So, pi is nothing but Rmin yeah, divided by Rmax. What is the Rmin value here? After assigning T1?
80.
Not 80.
Oh, so 50, 50, sir. 50.
Yeah, 50, yes. Divided by 153, right? So 50 divided by 153, you will get the value is 0.326. Right? You will get the value is 0.326. Right? So now what you will do? 0.326 means again the value lies in between pi L and pi H. Then you will again continue with MCT. You start with MCT, and as the value is in between pi L and pi H, you continue with MCT. So I need to calculate the completion time in the case of MCT. So 89 plus 285, how much you will get? Is it 374? I think you will get 374. Here you will get 233. Here you will get 351. Okay. So now these are completion time. Earliest completion time is this one. Okay. So you will cancel these two. Right. So you got earliest completion at 233. What is the ready time now? The ready time is now 89 to 33 and 50. Right. Now again calculate pi. Pi is R min by R max. What is R min? R min is 50. R max is 233. How much you will get? 50 divided by 2,
21.
0.21. Still it is in the range of pi L to pi h. So you need not worry. You continue with MCT. So T3 I am taking 189, 290 and 76. So how much you will get? 8, 7, 2, 3, 2, 523. This is, I think, 126. Right? So you got, this is the completion time. You will choose the minimum completion time. Minimum is this one. You need to cancel these two out. So completion ready time can be considered as what? 89, 233 and 126. Right? Calculate the pi value again. Pi is R min by R max. R min is, I think, 89 divided by R max is 233. How much you are getting? 89 divided by 233.
0.38.
0.38. So again it is in the range. Apply MCT. So T4 I am taking. T4 is taking 60, 97, 115. So it is 9, 1, 9. This is 14, right? This is 0 and 9, 4 is 3, 3, 0, 1, 4, 2. Okay. So the minimum one is 149. Okay. So you can calculate again. The updated ready time is 149, 149, 233 and 126. Okay. So now you go for T5. T5 is, okay, we need to calculate pi now again. So pi is R min by R max. R min is 126. R max is 233. How much you are getting?
0.54.
Point
4.
0.54, right? 54 means you will continue with MCT only, right? It is not exceeding the limit. So 135, 367, 37. So 4, then it is 8, 2, 0, 1, then 0, then this is I think 6, then 3 and 1. 8, 6, 1, 6. So minimum is this one, right? So the make a spin you are getting in C1, C2, C3 is first case you will get 149, second case you will get 233, then 163. Right? Then again here if you calculate, if it is in the range of this one, then you will continue with MCT only. But if it is outside greater than pi L, then you will change the mode to MET. Right? So as I said earlier, that if there are 1,000 tasks are there, there is only switching and number of times switch from MET to MCT is only 2 times. That's why with this small example, it is very difficult, in fact, to observe this type of peculiarity, right? Changing from MET to MCT, right? Okay, so this is all about all the 5 different algorithms, online algorithms or immediate algorithms. And I'll tell you about the data set and I'll also show you some of the implementation if time permits in the afternoon lecture. Okay. So we'll stop here. If you have any question, you can ask.